Hi, my name is Andressa Nakao. I'm a postdoc at NTNU Norway, and I'm also a member of the REALISE project research team. REALISE is a project sponsored by the European Union in 2020, and one of its focus is the decarbonization of refineries through carbon capture, usage, and storage. I'm here today to present the work Assessment of CO2 capture from multiple point source with a single regeneration column for efficient operation in refineries. This presentation is divided in 5 talks. First, a brief introduction about the refinery design will be presented. It will be followed by an overview of the study cases of this work, and it will also be presented the assumptions and parameters chosen for the sizing and cost estimation step. Finally, the discussion of the results and conclusions that we have made. The refining industry is a highly energy-intensive sector with direct CO2 emission. They are responsible for 6% of the total CO2 emission from stationary sources. In other words, 0.8 billion tons of CO2 are emitted per year. Unfortunately, in current studies, they only focus on the major CO2 stacks at a refinery, which results in only 50 to 6% of the CO2 is captured. One question that you should do is how can we increase this number? The refinery scenario can be described as an industrial cluster with multiple emission points. This means it has different values of flow gas rate with various CO2 content. How to deal with these different amounts of source? Dealing with a multi-source CO2 emitted at refineries is a complex optimization problem. This means that you should not only be concerned about the size and the cost estimation. For studying its feasibility, we should include in our study parameters and restrictions like the restriction of the available area, the distance between the sources, and the ease of the operation. Which should be the alternatives to deal with this case? The first alternative, and in this work we're going to call case 1, it would be the installation of complete CO2 capture plant for each source. Each source has a different CO2 content and a different molar flow, so each plant will have a different area requirement and a cost. The available area and the ease of the operation will influence the feasibility of each case. The distance between each stack doesn't have influence on the costs. The second alternative, and in this work we're going to call case 2, it would be the installation of one CO2 capture plant for the whole refinery. The size of the absorber in the strip will be increasing. In this case, the cost of some units and the utilities could have some restriction depending on the volume of the source. The available area and the distance between each stack should be incorporated on its evaluation. The third alternative, in this work will be called case 3, is the multiple absorber and single strip approach. The present work has as main purpose to present the multiple absorber and the single strip approach as an alternative to deal with industrial clusters which has multiple CO2 sources as the refinery, and also open the discussion about which parameters and restrictions that should be considered in this case. In this work, the operating condition of the absorber is slightly different from the case 1. This alternative can be a better solution if the available area close to the source is limited. In this case, the distance between the sources has influence on the cost. For the present work, it was created a case of study with 2 different stacks from a real refinery, and the suggested alternatives were simulated. The solvent used is MEA 38%, and the CO2 capture rate was fixed as 90% for each emission source. The software used was CO2 Syn developed by Syntef. For this work, you will select 3 different sources of CO2 emitted from a real refinery. Source A was based on a combined heat and power plant. Source B was based on a crude distillation unit, and Source C was based on a catalytic reforming unit. They have different CO2 content and different molar flow rates. For the equipment sizing step, it was made some assumptions that is presented now. For the cost estimation, we also did some assumptions that I'm showing now. The equipment and installation cost shows that case 3, the multiple absorber and one single stripper delivers CO2 with the lowest cost. This result was expected. For this study case, the absorber was the most expensive equipment, followed by the lean-rich exchanger. In the process plant cost tab, I would like to make a closer look on case 1 and case 3. In this slide, it shows some specifications of each stack CO2 capture plant of case 1. I would like to highlight the values of the lean load obtained and the ratio LG to achieve the CO2 capture rate of 9%. The main difference of case 1 and case 3 will be the status of the lean loading. In case 1, this value is specific for each source. As I said in the previous slide, I would like to make a closer look between case 1 and 3. In this slide, you can find the specifications of CO2 capture plant of case 2 and case 3. In case 3, the value of the lean load is the same for all the absorbers. To reach the CO2 capture rate of 90% in this case, it was necessary to increase the L over G and the specific rebody Dutch value. Although the absorption column has the same size, a different value of the lean load affects the thermodynamics of the process, demanding different conditions. I choose to go for the L over G and the specific rebody Dutch path to obtain the same capture rate. But this fact leads to a question. When you have a multiple CO2 sources and have a fixed lean load, which should be the best direction for obtaining the optimum point for the cost? To reinforce the previous discussion, in this slide you can find the flow sheet of case 1 and case 3. In case 1, each absorber has its own stripper, resulting in a lean load for each case. In case 3, the process has only one stripper. Then the lean load is fixed for all absorber and the CO2 capture rate has to be recalculated for each absorber. The present work also made the operating cost of each case. This slide shows the syn cost per ton of CO2 capture for different sources of syn. If the refinery has waste heat available, the cost would be reduced. The OPEX depend on the location and of the available resource for the plant. But it can affect the feasibility of a plant and the choice about which alternative you should choose. Based on the syn cost, case 1 delivers CO2 with the lower cost. Finally, the total cost. This slide shows the total cost based on the waste heat, but the behavior of the cost is the same for each source of steam. Case 3 delivers the CO2 with the lower cost, as we expected. Conclusions. The multiple absorber one-strip approach showed to be preferable option for the multiple CO2 source case study. However, the results are depend on the flue gas flows and the CO2 contents, the distance between the source, the available area at the industrial cluster, and the solvent. Finally, OPEX depend on the location, the available resource, and effects on the feasibility of the CO2 capture. This work was the first step of one of REALISE project task. The main purpose of this work was open the discussion about the multiple absorber and single stripper approach, recognize some difficulty on the process simulation and plan which directions are better to improve this optimization. The next steps would be obtain more results for simulation with different range of CO2 content, increase the number of stacks to be treated, improve the simulation flow sheet with more units related to the CO2 capture plan, and finally apply the realized solvent on the simulations. These are the references used in this work. Thank you for listening. My name is Andressa Nakao. This is email. If you have any question, you can send me. And thank you very much for your attention. Acknowledgement. In this part, I would like also to thank a special thanks for Juliana and Jasper from TNO and Hanna from NTNU. It is an amazing experience to work with you guys. Thank you very much for all the patience and all the learning. And I also would like to thank you, Andrew from Syntev, for all the helping on the CO2 simulations. Thank you very much.